Wait. And yeah, recording has been started now. Yes, again, very good evening to all of you. Let us begin without wasting much time. It is already 7:30. Fourth chapter, the comparative analysis of VO2 and ITO based electro absorption modulators. In reading session number 4. Over to you, Himanshu.
Okay, a very good evening to all of you. So today we are going to read the chapter 4 of our thesis, and the title of the chapter 4 is Comparative Analysis of Vanadium Dioxide and Indenting Oxide based electro-absorption modulators. So, beginning from the introduction, in recent times, plasmonic based optical modulators have led to the development of a hybrid class of miniaturized devices which can be incorporated with CMOS technology. Reference number 3, 25, and 55. These devices combine the electronic and photonic domains. Various silicon optical modulators have been developed to date with innovative designs like a micro ring resonator, micro Dix, Mach-Zehnder interferometer. Reference number 65 to 68. However, these devices have an impression of a large device footprint of around 5 micrometer micro ring radius, reference number 65, 1.75 micrometer micro Dix radius, reference number 66. Plasmonic materials based optical modulators have been developed to overcome a large device footprint, typically 500 nanometer waveguide length, reference 69. The plasmonic materials are index modulated materials that change their refractive index depending on the potential being, such as vanadium dioxide, gallium zinc oxide, indenting oxide, and graphene. Reference number 53, 57, 58, 69. Recently, vanadium dioxide and indium oxide have attracted much attention in the field of optoelectronics because of their phase transition characteristics and unique epsilon near zero ENZ characteristics, respectively. Reference number 9, 11, 57, 69. The integration of vanadium dioxide and indium oxide into the silicon waveguide has been intensively investigated to introduce new functionalities and realization of future potential for miniature photonic devices. Reference number 8, 9, 11, 51, 57, 70. The metal insulator phase transition in vanadium dioxide can be induced by an optical or electrical energy slash potential applied on a picosecond timescale. Reference number 70. In this chapter, two different plasmonic materials, vanadium dioxide and indium oxide, is used to design the electro-absorption modulators (EAMs), and their comparative analysis is done in terms of their performance matrices. Now, coming to section 4.2, material characteristics of vanadium dioxide (VO2). VO2 is an inorganic compound. It has a phase transition very close to room temperature, 66 to 75 degrees Celsius. Reference number 45. In this transition, VO2 transforms from a monoclinic to a tetragonal crystal structure, accompanied by significant changes in electrical and optical behavior. It is not uncommon to observe changes in the resistivity of more than 4 orders of magnitude as the temperature is cycled through the phase transition. With bandgap energy of equivalent to 0.6 to 0.7 electron volt, the semiconductor phase shows a high infrared transmittance. VO2 is the most extensively used of various vanadium oxides. This material is of particular interest both for scientific investigation and for use in various technological applications because its transition temperature of 66 to 75 degrees Celsius is nearest to the room temperature of all the vanadium oxides, and because its optical properties change appreciably in the visible and near infrared ranges of the spectrum during this transition. Also, vanadium dioxide is used in many applications. Reference 71. For example, erasable optical storage schemes have arisen based on VO2. Thin film threshold switching devices have been proposed based on the oxide's Joule heating, when an external voltage is applied, reference 45. Furthermore, the refractive index of vanadium dioxide in the metallic state and insulating state at 1550 nanometer communication wavelength has been taken in the simulation from experimentally obtained results of a VO2 thin film on silicon as shown in table 4.1, reference 72. Now coming to section 4.3, design of plasmonic material based electro absorption modulator. Hello? Sorry, am I audible?
Yes, sir.
Yes, you are.
Okay.
Yes.
Actually, sir is not changing in the page. That's why I have stopped. Maybe some network issue. So basically, for this section 4.2 shows the material characteristic of vanadium dioxide. So VO2 is termed as vanadium dioxide. So here in section 4.2, we have one table, that is table 4.1. This table 4.1 shows the refractive index of vanadium dioxide for metallic state and insulating state. And the metal state is termed as off state, and the insulator state is termed as on state. So the part of the refractive index, that is the real part and the imaginary part, is shown for both the states, that is the metallic state and insulator state, in table 4.1. So now coming to section 4.3, design of plasmonic material based electro absorption modulator. Sir, can you go to 4.3, section 4.3, design of plasmonic material based electro absorption modulator? So section 4.3, the previous section. Okay. Okay, let me start from this section 4.3.1, vanadium dioxide based modulator. So here in okay, everyone give me an excuse for 2 minutes. I will call Arya sir. So what is happening actually, even I don't know.
Hello, can you hear me?
Yes, sir.
Yes, sir.
Okay, okay. Thank you so much. Thank you so much. Yeah, sorry, there was an emergency call, and I could not hear. I have to mute it. Yeah, which section you are talking about, Himanshu? 4 point
4.3, sir.
4.3, 4.31, or which one? Yeah, this one. Okay, this one. Over to you, Himanshu, if you can hear me. Himanshu is here.
Yes, sir. Am I audible?
Yeah, you are very much audible. Please go ahead.
Okay. So section 4.3, design of plasmonic material-based electro-absorption modulator. In this section, two different compact nanoscale plasmonic material, vanadium dioxide and indenting oxide base EAMs with the same structural parameters are designed and investigated. The device consists of a silicon waveguide comprising of plasmonic material placed above a bulk silica substrate. The light propagating through the waveguide achieves strong field confinement in the presence of a plasmonic material along with the dielectric material when an electric field is introduced. The comparative analysis of both the devices in terms of their performances is investigated at a low loss optical communication window at 1550 nanometer. The devices under investigation shows enhanced performance in terms of insertion loss, extinction ratio, and figure of merit by applying a rigorous finite element method. A commercial FEM solver, COMSOL Multiphysics, is used to carry out the simulation results. Reference 48. Now, section 4.3.1, VO2 base modulator, vanadium dioxide based modulator. The VO2 base electroabsorption modulator consists of a Si plasmonic dielectric Si layer upon a silica substrate. Here, VO2 is used as a plasmonic material. The waveguide has a width WSI of 400 nanometer to support single TM mode, and the thickness of vanadium dioxide is 10 nanometer, as shown in figure 4.1. The thickness of the dielectric material, that is silicon dioxide, is 5 nanometer. Silicon dioxide is used as a cladding material and as a dielectric spacer. The length of the waveguide is 500 nanometer. Also, the electrodes are placed hundreds of nanometers away to avoid absorption and for biasing purpose. So 700 nanometer. It is kept away for biasing purpose. The vanadium dioxide is a plasmonic material where the phase transition is accompanied by a change of index, which leads to the guidance of the optical modes inside the waveguide. Reference number 72 to reference number 74. So figure 4.1 shows the cross-sectional view of the plasmonic material based electro-absorption modulator. So here the green color indicates the plasmonic material, which is vanadium dioxide in this figure, and the black color indicates the dielectric material, which is silicon dioxide in this figure. And this orange color part is the silicon waveguide. So the plasmonic material and dielectric material is sandwiched in the silicon waveguide. And the blue color material indicates the SiO2, that is silicon dioxide, and the gold colors are placed hundreds of nanometer, that is 700 nanometers away for biasing purposes. The refractive index of VO2 in the metallic state and insulating state at 1550 nanometer communication wavelength has been taken in our simulation from experimentally obtained results of VO2 thin film on Si, as shown in figure table 4.1, reference 72. The refractive indices of silicon and silicon dioxide taken were 3.48 and 1.44 respectively, reference 69. So far fabrication is concerned, silicon waveguide can be grown on a silicon on insulator SOI wafer with a 160 nanometer thick Si layer on top of silica. The silica layer can be fabricated by using a plasma-enhanced chemical vapor deposition PECVD technique, reference 75. Also, the vanadium dioxide layer can be deposited into the waveguide using a pulse laser deposition PLD technique at 450 degrees Celsius, reference 72. The upper silicon layer can be deposited using a deep UV lithography process above the VO2 dielectric thin film, reference number 73 to 75. Since the EAM electro absorption modulators working principle is based on electronically controlled absorption of light, IL's insertion loss estimation becomes essential and inevitable to determine its switching characteristic. The IL is calculated minus 10 log 10 bracket output power by input power to obtain the optimum value for different parameters of the device. The cross-sectional view of the field intensity of TM polarized guided mode for VO2 based EM at the insulating condition on state and metallic condition off state is shown in figure 4.2. The figure 4.2 shows the cross-sectional view of the field intensity of TM polarized guided mode in VO2 based EM at on state and off state. So figure 4.2 shows two state, that is on state, where there is no obstacle and the plasmonic material which is sandwiched between the SI waveguide, it is not creating any obstruction. Therefore, the light is passing through the waveguide without any obstruction. Whereas in off state, due to the phase transition, most of the light is absorbed by the plasmonic material. Therefore, huge or you can say large maximum absorption is there in the plasmonic material area. Therefore, the light is not passing through the waveguide, which is because of absorption of light by the plasmonic material. So that's why it is termed as off state. So in off state, light is absorbed, and in on state, light is not absorbed. So basically, the difference is that the field intensity is low at off state as compared to on state because of the phase transition, which is accompanied by change in the index. In the on state, light is passed with minimum absorption, whereas in case of off state, light is maximally absorbed because of the insulating and the metallic state of the material, respectively, on applying an applied potential. In the simulation, 1550 nanometer is taken as the device's operating wavelength with a meshing element size of 10 nanometer. The input power is launched to the device by exciting the modes in the waveguide. The frequency domain field along with the power monitors is used to increase the power reaching the waveguide's end. The effect of an increase in the thickness of VO2 on the IL of the device is shown in figure 4.3a. At 10 nanometer thickness of VO2, an IL of 6.50 dB per micrometer was observed at off state. Further, increasing the thickness of VO2 from 20 nanometer to 50 nanometer, there is an increase in IL almost exponentially at the metallic state because of the abrupt rise in the accumulation of polarized light at the active layer interface. So here in figure 4.3, there are two figures. That is figure 4.3a shows the insertion loss of the device as a function of an increase in the thickness of vanadium dioxide, and the inset shows the field intensity of the TM polarized light at different thicknesses of VO2 for both on state and off state. So it means by increasing the thickness of vanadium dioxide inside the silicon waveguide, we are measuring the insertion loss at off state and on state. So what will be the insertion loss or IL at different thicknesses of vanadium dioxide? So here we have taken thickness from 10 nanometer to 15 nanometer. And this black line indicates the on state of the device, means where light is allowed to pass, and the red color line indicates the off state, where maximum light is absorbed by the plasmonic material. And the inset, we can see that on state and off state. So it shows the intensity of light at 20 nanometer, 30 nanometer, 14 nanometer, and 15 nanometer for both on state and off state. And in figure 4.3b, it shows the effect of insertion loss with increase in length. So what will be the effect, or what will be the insertion loss if we increase the length of the device? So here we have taken 500 nanometer to 2000 nanometer length, and then we are calculating what will be the loss at both on state and off state. And the inset shows the on state and off state of the device from top view. You can say this is a top view. So in on state, we can see that maximum light is allowed to pass, while in the off state, maximum light or most of the light is absorbed. So this is what on state and off state means. So now the thickness of VO2 has a minimum effect on the IL of the device because of the almost transparent insulating characteristic of VO2 at on-state with IL of 0.651 dB per micrometer at 10 nanometer thickness. The inset shows the intensity of the light at different thicknesses of vanadium dioxide for both on-state and off-state. The device requires a drive voltage of 16.3 volt because the electric field threshold for the VO2 phase transition is around 6.5 into 10 to the power 7 volt per meter. Reference number 76. At on state, the complex refractive index of VO2 is 3.21 plus I 0.26 at a wavelength of equals to lambda equals to 1550 nanometer, reference 75. The real part of the refractive index of vanadium dioxide N equals to 3.21 is approximately equal to that of Si 3.48. Thus, the waveguide properties change and behave like a dielectric waveguide, and the field is homogeneously distributed throughout the high index layer as shown in figure 4.2 on state. With an increase in the device's length, the IL increases for both on state and off state because IL is proportional to the device's length as shown in figure 4.3b. Therefore, to maintain a balance between the IL and ER, we choose 500 nanometer as the device's length. The field intensity at off state diminishes due to its phase transition characteristic from insulator to metallic state. However, in the on state, minimal change in the IL is observed as absorption of light is significantly less in the insulator state. So coming to figure 4.4, so figure 4.4a shows the IL as a function of change in waveguide width, that is WSI. And figure 4.4b shows the IL over the C-band wavelength ranging from 1500 nanometer to 1580 nanometer. And the inset of figure 4.4b shows the effect of TE and TM mode on the insertion loss of the device over the wavelength range. So if we come to figure 4.4a, it shows the effect of waveguide width on IL. That is, when we increase the waveguide width of the waveguide, what will be the insertion loss at on state and off state. So we have calculated the waveguide width from around 250 nanometer to around 500 nanometer. So from 250 to 500, we have increased the width of the waveguide, and we have observed, or we can say we have calculated the loss, that is IL, for both on state and off state. And here the red color line indicates the off state, and the black color line indicates the on state. And maximum loss for the off state is observed around say 400 nanometer waveguide width, maximum absorption. And everybody, now you can ask me why I am only calculating this on state and off state losses. So I'm calculating this on state and off state losses because this insertion loss is a very important and crucial parameters in the field of optical modulators. And if we know the losses at on state and off state, we can calculate the extinction ratio. And from this extinction ratio, we can calculate the figure of merit of the device. And these parameters are the main parameters which we are focusing on for an optical modulator. That is the insertion loss, extinction ratio, and figure of merit. So that's why we are calculating the on-state and off-state for the devices. And we are taking this device dimension like waveguide width, thicknesses, and then the length of the device. And then we are observing that what is the most optimum value for which we will get a suitable value for extinction ratio. So that's why we are calculating this on-state and off-state losses. So coming to figure 4.4b, here we have calculated the insertion loss over the entire wavelength range from 1500 nanometer to 1580 nanometer, which is also termed as C band. So here this red color line indicates the off-state losses and the black color line indicates the on-state losses. So at around 1550 nanometer, which is the wavelength which we have taken, so maximum insertion loss at off-state was observed around 6.5 dB, and maximum loss for the on-state at 1550 nanometer was observed around 0.65 dB per micrometer. And here the inset shows the loss for TE and TM mode. So this black line indicates the TE mode and the red color line indicates the TM mode. So we have calculated this loss for on state. Here for on state means this is the state where minimum absorption should be there. So in our case we have taken TM mode. We have taken TM mode because we can see that in TM mode loss is very less in on state, which we want. That's why we have taken TM mode as compared to TE mode, because in on state we don't want our light or the signal to get absorbed. We want our signal or light to get absorbed only in the off state. Since the higher value of TE mode is present in on state, therefore we go for TM mode in case of our modulator. And this red color is TM mode, where the loss is very less, which is around 0.65 dB per micrometer. And for TE mode, the loss is very high in on-state, which is around 5 dB per micrometer. That's why we have gone for TM mode in our case. So the effect of waveguide width on the IL of the device is shown in figure 4.4a. The maximum IL for the off state was 6.50 dB per micrometer at 400 nanometer waveguide width, while maintaining a low IL of 0.651 dB per micrometer at on state. However, the modes traveling inside the waveguide is affected by the waveguide width. Therefore, to achieve a maximum extinction ratio of 5.85 dB per micrometer, 400 nanometer is chosen as the waveguide width. The IL of VO2 base EM over the C band wavelength ranging from 1500 nanometer to 1580 nanometer is shown in figure 4.4b. With an increase in operating wavelength from 1500 nanometer to 1550 nanometer at off-state, IL changes almost minimum due to the minimum change in the refractive index of VO2 at the metallic state over this range. However, from 1550 nanometer to 1560 nanometer, the IL decreases as the refractive index of VO2 is affected by the increase in wavelength. At low loss optical window wavelength of lambda equals to 1550 nanometer, the maximum IL absorbed at the off state was 6.50 dB per micrometer, and for on state was 0.65 dB per micrometer. And ER IL off state minus IL on state of 5.85 dB per micrometer was calculated. The TM mode analysis has been used for the device because TE mode is not so prominent as shown in the inset of figure 4.4b. The IL incorporated by the device at on state is very high in TE mode, 5 dB per micrometer, compared to TM mode, 0.651 dB per micrometer at 1550 nanometer communication wavelength, as most of the energy in TE mode gets diffracted throughout the state.
Give a pause here, Himanshu.
Okay, sir.
Before going next, I would like to welcome Miss Ananya Hazarika, who is attending from Ohio State, from the United States of America. She is pursuing PhD from Cleveland State University. So she happened to be our Lightwave Communication System Laboratory member. Thank you, Ananya, and welcome.
Hello,
And
sir,
thank you for
and
giving
good
your
morning.
time. Good
Hello,
morning.
sir.
Very good morning.
Hello, everyone.
Yes, Ananda, you go ahead. You can speak. Over to you.
Hello, everyone. Actually, this timing is in morning. It's early morning in US. So I was unable to attend the earlier sessions of the PhD reading. So today is Sunday. So like, it's a great presentation by Himanshu.
Yeah, Ananda used to have early morning classes from 8:30. So,
8
and she
a.m.
has just joined
Yes, 8 a.m.
8 a.m. Okay, 8 a.m.
Yes, here
So,
we
being
have
in
classes from
this,
8 a.m.
okay, very good. So, some coursework is going on, or what kind of
Yes, I have
courses are
9
going on right
credits
now as a
courses.
PhD student?
Like,
Okay,
sir,
nine
I took
credit
two
course. How many
courses.
courses?
Yes, two courses are there,
Okay,
4 credits each, and I have to attend from 9:30 to till 5 p.m.
okay. And what is the department as well as what are the courses which you are pursuing?
Okay, sir. Right now, I'm pursuing main courses. One is advanced optimization, and the second one is modern controls. And third one is a doctoral research, which is 1 credit course. And for that, I'm doing my
Mhm.
like, research work under my advisor.
Okay, and in which department you are enrolled in Cleveland State University?
Yes, sir. My department is electrical and computer engineering, and my domain for research is communication track.
Okay,
And it is
okay.
focusing
Very
on
good.
the wireless
Thank you.
communication.
Very good. Very good. Nice to hear you. And we feel proud
Thank
also
you.
that
Thank you
our
so much.
member has reached there. So yeah, thank you so much. And actually, in nutshell, in this section, VU2 based optical modulator has been designed. That yeah, see in this figure, if we see this figure 4.1a, this is the generalized cross sectional view of plasmonic material based electro absorption modulator.
So,
So here 400 nanometer waveguide width is mentioned, then 340 nanometer waveguide height is mentioned, and other thicknesses of your plasmonic, dielectric, etc. But before noting all these value, we have to optimize. We have to characterize
yes.
what is the best, what is the optimum, say thickness. Suppose here thickness of VO2. What should be the optimum thickness of VO2 so that the material characteristics can be behave perfectly. What is meaning of perfectly here? That this modulator should work as a switch, as a perfect switch.
Okay.
Means in on state, light should pass. Means 100% light should pass. However, practically maybe 90%, 80%, something like that. But this is where we are trying to achieve our goal that it should tends towards 100%. And in off condition, complete light should be absorbed or no light should be available at the output. This is what is perfect switching action. How to achieve that? This plasmonic material has a unique characteristic that applying voltages, we can change its behavior drastically from dielectric or say insulating state to metallic state. When this plasmonic material is in the dielectric state, it means it will not absorb light at all. It means whatever light is coming at the input, complete light will be available after say 500 nanometer or passing through the entire length of the device at the output. Means it is just transparent. It is allowing go ahead. This light is at the input as well as the output light is available. That is the state. That is, but we are controlling electronically by applying potential, a particular potential, so that this modulator should be transparent in on state. However, when we want to switch off, closed, at that time, this plasmonic material will behave drastically different way. That is the metallic way. Metals absorb the light maximally. So in a figure at 4.3a, we can see in off condition, light is absorbed maximally. However, we want to observe that what should be the what should be this thickness, because we want to optimize this thickness. We suppose we choose 20 nanometer, then 30 nanometer, 40 nanometer, 50 nanometer. We are observing that lesser the thickness, more is the absorption. It is not wise decision to keep this width, VO2 width high. Okay, so you can see now the light is lesser absorbed. It means some light is available. Okay, with this graph we can see this is the bar graph of color pattern, volt per meter. So in first we are trying to optimize or trying to get the optimum value of VO2. In second one, we are trying to now optimize the length. Once we get the optimum value of say thickness as well as thickness, then we are trying to optimize this length. Okay, so top view also showing this convincingly that in on state light is visible. Of course, some absorption is there. That is what is a loss issue. That is where we have to minimize this loss. Minimizing this loss in on condition means we are improving the efficiency of your device. And in off state, you see almost negligible light is there, but of course some light is there, means we are not able to achieve 100%, and that is not possible also. There is nothing as such 100%. Some practical cases are there. Okay, but it will serve our purpose, means your device is working as a switch on and off. That controlled mechanism is what is expected as a modulator. Now this after optimizing this thickness and second one was the length, now width, and at which wavelength your device is performing well. So more or less you see for C band its performance is good. Okay, so device performances in C band almost wavelength dependent, means your device can work for large range of wavelength. Any wavelength you set in the C band, it will perfectly work. That is the figure we want to establish here. And what should be the waveguide width? This width, optimum width, so that optimum switching can be absorbed. Optimum switching means on and off perfectly. This graph shows like that. So in nutshell, we are trying to tell that how efficiently we can control the property of plasmonic material, that is VO2, in on and off condition. That on condition by measuring insertion loss, extension ratio, and figure of merit in technical term. But these things are controlled by input parameters. What are those input parameters? Basically, that is the architectural design, the way we have learned yesterday in our chapter number 3. What may be the optimum architecture? Of course, there are variation of selecting proper material. Like in another example, we will look into ITO. This one is VO2. Later on, we can see graphene also, not in this thesis, if somebody else wants to work. So there other plasmonic material can be incorporated. So variation is there in terms of plasmonic material, but within plasmonic material, what best we can propose a design parameter to develop your optical modulator. I think this is the simple way. We want to design our device so that it should work as a perfect switch. For the optical signals. There are in electronic devices also, for C most inverters are there, that is also a switch. So in that also, with the help of CMOS inverters, we make different gates, then circuits, then system. There also we try to minimize the losses and other thing, of course, but at device level we try to decrease this channel width by taking other parameter. But important thing, as earlier also we have read, that whatever exercise we are going to do, its fabrication is CMOS compatible. That is the beauty of working in the field of silicon photonics. No need to establish or commission or invest huge money to establish foundries. Okay, same existing mature technology with small modification or appropriate modification, we can develop these devices. Okay, so any question we shall be happy to take up before coming on the ITO. So VO2 based optical modulator has been modeled thoroughly, keeping all parameters, taking the range of parameter and choosing the appropriate one. through graph we can see how its characteristics is varying. So this main parameter is the insertion loss, because ER and extension ratio and figure of merit, these are the derived value based on the insertion loss. That is why you will find lot of characteristics curve. X-axis are varying. On x-axis, in one case, width is there, wavelength is there, thickness is there, but on y-axis everywhere you will find IL. That is the insertion loss. That is the common. So reason is that other parameters are derived based on the insertion loss. That is why insertion loss calculation becomes very, very important. Yes, you can type the question into chat box also. We shall happy to take up. So if no question, then we can move further. Himanshu, over to you.
Yes, okay. So let us start section 4.3.2, ITO-based modulator. ITO is also a plasmonic material and compatible with existing CMOS technology, reference 9-1577. Like unique ENZ conditions and good electrical conductivity, the promising future of ITO makes it a suitable material for optical modulators, reference 9-55. The same structural design as shown in figure 4.1 is used with ITO as the plasmonic material and hafnium dioxide, HFO2, as a dielectric material. When potential is applied to the ITO layer, the refractive index is affected by the capacitively induced accumulation layer, thereby incurring a waveguide loss, reference 8. The refractive index associated with the device is varied with the aid of placing the ITO layer along with the dielectric material in the SI waveguide, forming a SI ITO dielectric SI stick upon a silica substrate, reference 8, reference 51. The majority of light is tightly confined around the stick when a potential is applied. To tolerate the high electric field induced with low biasing voltage, the dielectric material HFO2 is used. The refractive index of the device varies with the light ITO interaction. Alteration of the refractive index varies the IL of the device, triggered by applying a potential. Reference 9. The material characteristics of ITO can be defined by the Drude-Lorentz model, which gives the complex permittivity of ITO. Reference 51. So coming to figure 4.5, figure 4.5a shows the complex permittivity of ITO as a function of applied potential, and figure 4.5b shows the cross-sectional view of the field intensity of TM polarized guided mode in ITO-based EAM at on-state and off-state. So coming to figure 4.5a, it shows the permittivity with respect to voltage. That is, whenever the applied potential or voltage is varied, what will be the permittivity of the device, or how the potential will affect the permittivity, that is the real and the imaginary part of permittivity of ITO. So this graph has been shown previously also in chapter 2. So it's the same. So the real part of permittivity of ITO decreases with increase in potential, and the imaginary part, which is the red color line, increases. So at around 4.45 volt, that is whenever 4.45 potential is applied to ITO, the real part of permittivity of ITO reaches 0, which is known as epsilon naught near 0 condition. So at this point, or at this condition, or at this potential, that is 4.45 volt, the phase or the behavior of the ITO material changes from a dielectric to a metallic state. So we are using this 4.45 volt as the applied potential in order to change the phase or the state of the material, that is the ITO material. And therefore it is termed as ENZ, epsilon near 0 condition, because the permittivity is denoted by epsilon naught. So whenever epsilon naught is equals to 0, it is termed as epsilon naught or epsilon near 0 condition. And coming to 4.5b, it shows the on-state and off-state of the device. It means whenever the potential is applied, that is 4.45 volt to the ITO material, the phase of the material changes from a dielectric to a metallic state. So when it becomes, or when it changes its phase from dielectric to metallic, the light is absorbed by the plasmonic material, which is ITO in this case at off state. So most of the light, or maximum light we can say, is absorbed at off state whenever a potential is applied. However, when no potential is applied, which is termed as on-state, maximum light is allowed to pass through the waveguide, so which is indicated in on-state in figure 4.5b.
Yes.
So yeah, next, the Drude-Lorentz model is used to calculate the material characteristic of ITO from equation 3.1, 3.2, and 3.3 of chapter 3. The value of material parameters like KHFO2, THCC, THFO2, and NOT, and VG taken for the device are same as the modified sidewall angle base EM in chapter 3. The complex permittivity of ITO concerning the potential applied is shown in figure 4.5a. The imaginary part of ITO's permittivity, IM epsilon ITO, increases and the real part, RE epsilon ITO, decreases with an increase in the potential, which is calculated from equation 3.1 chapter 3. Real part of the real permittivity part of ITO, that is RE epsilon ITO, reaches zero at a particular potential, that is 4.45 volt, which is referred to as ENZ condition. Reference 9. At this condition, the phase of ITO changes from a pure dielectric to a metallic state. The effect of VG, applied potential, on the change in the electron concentration of ITO was investigated by Thomas Fermi screening theory, reference number 5960. The refractive index of ITO is influenced by the change in permittivity, which can be calculated by epsilon r equals to n minus ik whole square, where the real part and imaginary part of ITO's refractive index is denoted by n and k. The ITO base EAM structure consists of Si, ITO, HFO2, Si layer stacked upon a silica substrate. The lower part of the Si waveguide width and height is 280 nanometer and 160 nanometer, which can be fabricated by using a fluorine-based dry etching technique and a SiO2 hard mask. Reference number 61. An atomic layer deposition, ALD grown ITO lamella, can be transferred to the lower Si waveguide along with a thin layer of hafnium dioxide of 5 nanometer. Reference 8. The Si layer above the HFO2 ITO interface can be deposited by deep UV lithography method together with a plasma-enhanced chemical vapor deposition method, PECVD. Reference 8, 51, 62. Figure 4.5b shows the field intensity of the guided mode at on-state and off-state inside the waveguide. The on-state corresponds to 0 volt and the off-state corresponds to 4.45 volt. The majority of light is confined at the active layer interface at off-state because of the ENZ condition, where most of the electromagnetic energy is limited to the aggregation layer within the waveguide. Reference 8. Moreover, in on-state, the light travels through the high-index layer undisturbed due to the active layer's minimal absorption of light. Thus, it gives a tuning capability of light inside the waveguide concerning the applied potential. The effect of an increase in thickness of ITO on the insertion loss of the device is shown in figure 4.6a. At on-state, the change in IL is minimal, with an increase in ITO thickness as the minimum amount of light is absorbed in the absence of applied potential. Reference 9. On the other hand, at off-state, most electromagnetic energy moves away from the high-index Si waveguide and drawn towards the active layer because of the ENZ conditions. With further increase in the thickness, IL decreases slightly to 2.57 dB per micrometer at 20 nanometer thickness, and then increases as shown in figure 4.6a. Therefore, to maintain a good ER and FOM relation, 10 nanometer is chosen as a thickness as the ITO thickness. The inset shows the intensity of the guided mode at different thicknesses of ITO at on-state and off-state. Also, with an increase in length, the IL increases as the device's loss is proportional to the length, as shown in figure 4.6b, reference 8. The inset shows the propagation of light at on-state and off-state for a 2000 nanometer long device. Figure 4.6c shows the effect of change in the waveguide width on the device's insertion loss. At off-state, the IL increases with an increase in waveguide width and reaches 3.09 dB per micrometer, at 400 nanometer. Further, the IL insertion loss remains constant with an increase in the waveguide width. So now coming to uh, 4.6, figure 4.6. Figure 4.6a shows the effect of change in ITO thickness on the IL of the device. The inset shows the field intensity of the guided mode at different thicknesses of ITO. So in figure 4.6a, we can see the thickness of ITO versus IL, that is insertion loss in dB per micrometer. Here, different thicknesses from 5 nanometer to 15 nanometer is taken for the ITO layer. And then we have calculated the on-state and off-state for all the thicknesses. And the inset shows the field intensity of the guided mode for both the on-state and off-state at different thicknesses of ITO, that is 20 nanometer, 30 nanometer, 40 nanometer, and 15 nanometer. So here, the thickness of the ITO we have taken is 10 nanometer. We have chosen 10 nanometer as the thickness of ITO because if we see the red color line, that is the off state, the insertion loss decreases from 10 nanometer to 20 nanometer drastically, and again it increases from 20 nanometer to 50 nanometer. So what we want is that we want maximum absorption at lower thicknesses of ITO. We can go for 15 nanometer thickness of ITO, but what will happen is that if you go for 15 nanometer thickness of ITO, then it will increase the dimension of the ITO layer, that is from 10 nanometer to 15 nanometer. So there is a trade-off. If we want maximum absorption, then we will have to go for maximum thickness. While if we go for minimum thickness, that is 10 nanometer, we are getting a maximum absorption at offstate of around 3.09. So maximum absorption at lower dimension or lower thickness of ITO is observed at 10 nanometer. That's why we have chosen 10 nanometer as the thickness of ITO, where we have got around 3.09 dB per micrometer of insertion loss at offstate and around 0.025 dB per micrometer at onstate, which gives a better extinction ratio. And coming to 4.6b, it shows the effect of change in length of the device on the IL. The insert shows the field intensity of the polarized guided mode along the length of the device. Here, with increase in length, the IL increases as insertion loss is proportional to increase in length, and the insert shows the on-state and off-state of the device. And coming to figure 4.6c, it shows the waveguide width versus the IL. So with increase in waveguide width, how it will affect the insertion loss of the device is shown in figure 4.6c. Here we have taken the width from around 250 nanometer to 500 nanometer, and then we have calculated the loss at on-state and off-state. Here we can see that the loss at off-state increases drastically or abruptly from 250 nanometer to around 400 nanometer, but after reaching 400 nanometer it almost remains constant till 500 nanometer. Here we have chosen 400 nanometer as the waveguide width because at 400 nanometer we are getting maximum absorption at off state. Therefore, we will get a maximum value of ER. So the higher the difference between the off-state and on-state, the higher the value of ER, that is the extinction ratio, we will get. That's why we have chosen this 400 nanometer as the waveguide width for our device. And figure 4.6, it shows the insertion loss over the entire C-band wavelength range. That is from 500 nanometer to 580 nanometer for both on-state and off-state. So at around 1550 nanometer, which is the low loss optical window, at 1550 nanometer, we have got insertion loss of around 3.09 dB per micrometer at offstate, and at onstate we have got around 0.025 dB per micrometer.
Any question up to in this while understanding this graph? I try to annotate the way Himanshu was telling. I think audience could follow it. Is it visible clearly? Anyone can respond? These graphs are visible?
Yes, sir.
Okay, thank you. So again, same exercise here. Making efficient switching device based on the ITO. So thickness has been optimized, length has been optimized, waveguide width has been optimized, and at what wavelength, at what operating wavelength, we are going to suggest the device parameter. Okay, so these are the four variables: thickness, length, width, and wavelength. Okay, and however y-axis, that is the insertion loss, as well as TE and TM mode also. So now we have already established that this entire device works TM mode in a better way, but through this intensity profile, we are trying to tell that how light is visually we can inspect. Okay, yeah. So yeah, let us move further.
Okay. So starting from width, because maximum light confinement in the active layer is achieved at 400 nanometer waveguide width. Further increasing the waveguide width has minimal effect on the IL of the device. Also, defining the ER as the difference between the off state 3.09 dB per micrometer and on state 0.025 dB per micrometer losses, maximum ER, that is 3.07 dB per micrometer, is achieved at 400 nanometer waveguide width for the device. Figure 4.6d shows the IL of the device over the entire C-band wavelength ranging from 1500 nanometer to 1580 nanometer. At 1550 nanometer communication wavelength, the IL for the on-state and off-state was 0.025 dB per micrometer and 3.09 dB per micrometer. So coming to section 4.4,
Yeah,
comparative analysis.
before this, any question? Let us ask our something. Anyone? We are here 9 people total. We can ask question in chat box also. That shall be great. If no, I think this is the last section. Comparison. Once we have designed or optimized this VO2 and ITO base, so this section is how to compare these results, because comparison tells merits and demerits are at which reason or for what cost these devices can be more suitable compared to one or another. Okay, how many pages are there still?
So 1, 2, 3, 4 pages are there.
4 pages. Okay, this is the only table. I think hardly 3 pages then. Okay, yeah. Last one is the summary. Yes. Over to you, Himanshu.
Okay, section 4.4, comparative analysis of vanadium dioxide and indium tin oxide based electro-absorption modulators. The effect of change in the structural parameters on the device's performance in terms of IL has been shown in section 4.3. The investigated vanadium dioxide and indium tin oxide based electro-absorption modulators are compared in terms of their performance matrices in this section. Also, both the EAMs are compared with contemporary devices. Section 4.4.1, results and discussion. The vanadium dioxide and indium tin oxide base EAMs are designed using the same structural parameters for comparison. The ER and FOM for the devices can be calculated from equation 2.13 and 2.14, chapter 2. The ER can be calculated from the off-state and on-state losses of the device. The ER for vanadium dioxide and indium tin oxide based electro-absorption modulator was calculated to be 5.85 dB per micrometer and 3.07 dB per micrometer respectively at 1550 nanometer application wavelength as shown in figure 4.7a. Also, the FOM figure of merit for the devices was 8.98 for vanadium dioxide based EAM and 122 for ITO based EAM, as shown in figure 4.7b. The efficiency of the ITO based EAM is better in terms of ER, IL, and FOM as compared to Sorge et al. Reference 59 and Lee et al. Reference 64. The performance improvement is due to the change in the structural parameters. Also, the vanadium dioxide based EAM shows better ER and FOM performance than most of the devices shown in table 4.2, reference 12, reference 13, reference 78. The device modulation speed can be calculated from equation 3.4 chapter 3, and it was observed to be 8.84 GHz for ITO based EM and 52.6 GHz for vanadium dioxide based EM respectively. The resistance was assumed to be 500 ohm, reference 77, and the capacitance of the VO2 and ITO based EMs were calculated to be 6.05 femtofarad and 36 femtofarad. Also, key bit of VO2 and ITO based EMs were 400 femtojoule per bit and 178 femtojoule per bit respectively, as calculated from equation 2.15 chapter 2. Both the investigated devices have been optimized by exploring the device parameters like the weight of the waveguide, the thickness of the plasmonic material, and the length of the device.
So you can see this table 4.2. In this table, various contemporary this plasmonic material based devices have been considered based on common parameter, that is active materials. What is the active material here? Plasmonic material. Like these sets have been have considered this ITO, and these sets have considered VO2. So, and insertion loss, extension ratio, figure of merit, energy consumption per bit. Basically, unless we fix a common parameter, then only we shall able to compare. So that is why this is essential. This is how we can compare. So this values of different parameters has been taken from the reference 8, then reference 59, 64, 79, 13, 12, 80, 78, and so on. So in reference we can look into what are those are. That is why extensive literature survey and understanding what other people are working in the same field, that kind of knowledge we should have. Then only we can target, we can improve, because sometimes they used to mention the methodology also, that kind of methodology or scope for future work they used to tell. So that kind of thrust area we can take up. But we, in order to qualify your work to get published in quality journal or good impact factor journal, that kind of nowadays exercise is essential. Means comparison, they used to see how much improvement you could achieve compared to others. Why your article should be published unless it provides some extra development in terms of performance improvement, something like that. So this is the results of ITO based, and this is the result of VO2 based. And after that, some remarks has been given, not necessarily in terms of every parameter your proposed device is going to supersede for ITO as well as for VO2, but in certain cases, then there we have to justify why sometimes their results is superior and our is inferior, or why our is superior and their is inferior. Okay, so this is the things. And later on, yeah, in order to compare that ER extension ratio for both within that our results, like means we are proposing two optical monitor, one is the VO2 and another one is the ITO based. So can we compare these two within that? So these graphs are telling 4.7, A and B are telling about that one. Okay, Himanshu, over to you. Himanshu, can you hear? Over to you.
Yes, sir, I can hear. Okay, so coming to figure 4.7, figure 4.7a shows the ER as a function of wavelength for both vanadium dioxide and indenting oxide based electro absorption modulator. In figure 4.7a, it shows the extinction ratio for both the vanadium dioxide and indenting oxide over the wavelength range from 500 nanometer to 1580 nanometer. So here the extinction ratio is calculated from the on-state and off-state losses of each device. So for the on-state and off-state, from the on-state and off-state losses of VO2, we have calculated the ER from the formula extinction ratio equals to insertion loss at off-state minus extinction ratio minus insertion loss at on-state. Similarly, The extinction ratio for both the devices, that is VO2 and ITO, is shown in figure 4.7a, and we have compared the result, and we have seen that at 1550 nanometer, the extinction ratio for VO2 was around 5.85 dB per micrometer, and the extinction ratio for indium tin oxide was around 3.07 dB per micrometer at 1550 nanometer wavelength. Similarly, the figure of merit for both the devices, that is vanadium dioxide and indium tin oxide, is shown in figure 4.7b over the entire wavelength range from 1500 nanometer to 1580 nanometer. And at 1550 nanometer, the figure of merit for vanadium dioxide was found to be 8.98, and for indium tin oxide, it was around 122. So these results are shown in figure 4.7a and 4.7b. So now coming to the text.
Yeah, just a second. In 7.4b, you see we have two axes for same value like figure of merit, and y1 suppose, and this is y2, and this is x-axis. X-axis is common, that is the wavelength. But since values are so large for VO2 and ITO, that is why we have plotted on two y graphs, that is y1 for FOM of VO2 based, and y2 of FOM for ITO based. Okay, so you see red color. That is why here it is shown like that. So one should know how to draw these these graphs also whenever such situation occurs, because on the same parameter you see this value is very high. 100, how much?
122.
122, and here maximum value is 10, so it is difficult to show. Why we are doing like that? We are stretching so that even small variation which is occurring near to this near to, so 8 near to 9, in case of VO2 can be shown similarly for this value. So in order to depict even small information, minute information, we have we have zoom it in this case. That is why it was necessary to use two y-axis, that is y1 and y2. So such kind of skill also we have to develop while doing research work, etc. So with this, which portion you are going to read? Text, as far as
The
text,
text, yes, sir.
this much
Text.
will. Okay, yeah.
Okay. Using the FEM-based full wave propagation method along with mode analysis of the device present in COMSOL multiphysics, that the dimensions of the waveguide is well suited to work in a regime considered to be a single mode with low propagation losses at the communication wavelength of 1550 nanometer. The ER of PO2 based EAM is better than ITO based EAM. Also, in terms of FOM, the ITO based EAM is better than VO2 based EAM. Furthermore, the performance of both the devices can be enhanced in terms of IL, ER, and FOM by making structural design changes and also by realizing different plasmonic materials within the device with the trade-off of high IL, complex and large device footprint.
Yeah, thank you. So again, we have completed this chapter 4, a contributory chapter 4, and we are now just about to complete our this big task, a kind of monotonous task, reading the PhD thesis, as we used to tell. See, our purpose is here not to make the things complex. Instead, we want to tell that even after reading the thesis, what is the in nutshell? In nutshell, that we want to design a device of which switching characteristics can be controlled. Switching characteristics means this on and off condition. So what kind of design parameter you can propose so that efficient switching mechanism can be done. So this is in nutshell. Other things are supplementary and results to advocate or to give the evidences to prove your logic. But my purpose is that, or our intention is that every participant who are here should get out of that something like that. What we are trying to say, we are trying to say that in simple word, we are proposing a device, optical device, which should work as an efficient switching so that modulation can be done. For that, what are the design parameters through which you can play with, and what are the methods through which we can apply to do so, like a finite element method using COMSOL multiphysics. And now COMSOL multiphysics is freely available through iSTEM, through iSTEM platform. Everyone can do. So we want to make realize you that whatever Himanshu has achieved, you can also achieve. It is nothing like that. It is beyond your reach. It's not like that. Okay, only there is a need of putting honest effort, continuous effort, means widening your knowledge. Doing research is one thing, but you getting information from literature survey, becoming up to date information, that is also very important aspect. This is what we are trying to do. Other thing is that, as we used to tell, that we want to recognize the outcomes of light wave communication system, as well as we want to tell also that what we are actually doing as a researcher in a team, because most of the time we could not get in a platform, or sometimes we are not able to attract the researchers from other part of the country, that what we are doing. Even publications is there, but I have doubt people must be reading the way, because of sometimes brand name. We do not belong to say NIT or IITs or something like that. So okay, some university teachers or researchers have published, or that may be kind of like that, but it's not. We have seen that how much comparison we have done extensively, and the same thing they also used to do. I have attended many PhD thesis defense, and we used to see the contribution of the research. Time wise also, here relatively in light wave communication system laboratory, lesser burden on student have been given compared to topmost universities. So with this, I would like to thank. And chapter 6 is hardly 3-4 pages, and chapter 5 is, yes, contributory, the way this chapter is there, but interesting, and that has also come as a publication. So I think 80%, Himanshu, we have covered now 80% of our
Yes,
thing.
around 80%.
Sorry.
Yes, sir, around 80%.
I would say 60, how much pages? 67, 66 pages we have covered, and total pages we have how much? This is 85 pages. So already 67 pages, 80 pages. So just only, I think tomorrow we can finish, including chapter 6 also, instead of going another day. So we can take chapter 5 as well as chapter 6 tomorrow. Okay,
Okay, sir.
but this long journey can be given a full stop. So with this, I would like to thank you again. Okay, and Himanshu, you should also express thanks to participants and new members. Basically, I would like to hear also new members who are there. They can introduce. We want to hear from them. Like Deep, uh, I can see Mr. Deep.
Yes, sir.
Can you little bit introduce yourself?
Hi, my name is Dibosho. I'm from Guwahati, Assam,
Yeah. Uh-huh.
and I'm now pursuing my MTech in EC in from Nehu, Shillong.
Okay. You are in third semester?
Yes, sir.
Okay, okay, very good. So who is your supervisor, current supervisor for dissertation work?
Sir Rajkishore Mudai, sir.
Okay, okay, Dr. Rajkishore Mudai. And Hirdar Das, who is the supervisor,
Yes, sir.
who is the
Sir
dissertation supervisor?
Sir
Deepanka
Nipanko
Boli?
Bora, sir.
Okay, Dr.
Nipanko.
Deepanka Boli. Very good, very good. So I think something you could learn from here, how to, you graph, literature survey, comparison work. You can apply this information in your area wherever you are working. Okay?
Okay, sir.
Okay, sir. Okay, then thank you so much. Himanshu, you want to say something?
Sir, the summary is left, sir. summary of
Oh,
the chapter.
yeah, sorry. You go ahead. Summary, yeah.
Okay, section 4.5 summary. The summary of this chapter is as follows. Section 4.1 gives a brief introduction to the contribution in the chapter and plasmonic material based EMs. Section 4.2 discusses the material characteristics of VO2 plasmonic material. The design of the EAM based on VO2 and ITO plasmonic material is discussed in section 4.3. Also, the effect of various structural parameters on the IL of both devices are discussed in this section. The comparative analysis of both the VO2 and ITO based EAMs are discussed in section 4.4. Two different EAMs have been designed and investigated using VO2 and ITO material with the same structural parameters and compared in terms of IL, ER, FOM, and EBIT. The IL is very low in ITO, 0.025 dB per micrometer based EAM as compared to VO2, 0.651 dB per micrometer based EAM in the Onstate. The VO2 based EAM shows better performance in terms of ER, 5.85 dB per micrometer than the ITO, 3.07 dB per micrometer based EAM. Also, both the devices shows better performance in terms of IL, ER, and FOM as compared to most of the devices shown in table 4.2.
Yeah, so finally we have completed. Sorry for this little bit left portion. Yeah, that's good. So let us give big hands to ourselves, including Himanshu. Thank you so much. And thank you all participants who have given their valuable time to be part of this reading session. So reading habits we have to also develop. So nowadays many things are available in ready-made and we do not read, particularly this thesis, etc. So hardly we read. So research article, textbook, books, thesis, etc. We should read. Please try to read. If not in isolation, let us read it collectively to understand, to deliberate. So brainstorming should be there. Okay, this kind of culture we have to develop. So with this, thank you so much for being here. And one can take, I think everyone can. I would request everyone should open their camera, and I want to take one snapshot. Okay, let me stop this presentation. Would you like to please open your camera to have a snap? एक फोटो लेना है. Good, deep. Nice to see Hriday. Yeah, Indrani, Himanshu, Mansi, Ananya. Wow, great. Mansi, everyone is waiting for you. Mansi Das,
Sir, my network is not working.
you try to on it. You try to on it, then we will see. We here no need to communicate as such. We wish to we wish to have only photograph. Yes, try whatever it is coming.
Yes, sir. My I on camera.
Okay, no problem. Thank you. Thank you so much for being here. And now we can sign off. Okay, so see you tomorrow. Last session we shall try to conclude. Okay, at least this thesis. Okay, nice to see you, Ananya. Next
Thank you,
time
sir.
you can, if you wish to talk, you can talk since you are in another country and very far away and there is a time gap. So if you wish to talk to other members, really we are excited to hear you. Deep, Hriday,
Yes, sir.
Mansi, Rani, you want to interact to Ananya? You can interact. This is a golden opportunity. Otherwise, you will not find. Okay. Indrani, you have any introduction things?
Yes.
You asked to Ananya what she has eaten. But
Yeah.
yeah,
But I don't have any questions right at the moment. But would it be all right if I contact you?
talk like a friend. Don't to have always
Yes,
question.
yes.
Ask what she used to. eat there. How is weather? Not necessarily always we should have a question and answer mode. Interact like.
How is the life there? I mean, did you get any culture shocks when you landed in the US?
The weather is really good. Uh, Sometimes the weather is
Is that
like
a
a
plus?
long.
Yeah.
Yes. Now it's summer, but I will start snowing after 1 or 2 months. The winter is terrible here.
Well, yeah, there's the heavy snowfall is always a problem. But
Yes,
it's
yes.
still better than sweltering in the heat. So I would say that that's a lot better.
So in Johnny, you are the final semester. In Johnny is the final semester.
No, I'm
You are
in
in
my
final
pre-final year. I'm in my third year.
Okay,
In the
okay.
fifth semester.
Okay, you are in the
Yeah.
fifth semester.
And how is everything else there? I mean, did you any problem in the food and everything? Did you get any sort of
Like,
you got very
like
spellbound when you
yes,
just landed there?
here we have some Indian stores and we buy the groceries and the food from there only. So we are cooking the food.
Oh, okay. So like home cooked for the most part.
Yes, home cooking. Yes.
And
And in the Indian
what
restaurants,
else did you?
if we want to go and have something Indian food from the Indian restaurants, the price is really high. So it costs around $20 to $25. So it's better to
Yeah,
bring the
that's
food
too
and cook
much.
in the room. Price
Yeah,
is too high.
yeah. So do you live in an apartment with everyone else, or do you live in the
Uh,
university dorm?
like my apartment is the straight opposite to my this university. I share my room with two other girls. Okay,
Okay.
it's just a 5 minutes walk from my apartment.
So did you know your roommates before, long before you joined the university, or it's just
Yes, yes,
they're all
yes.
new faces?
We contacted each other in some groups. So one of my roommate
Oh,
is doing job in Cleveland, and other is a master's girl
oh,
from CSU, same university.
oh, that's nice. Like familiarity is nice to
So,
some extent.
so how are your studies going on? Like, it's
It's
better
all
to
right.
get involved in such
Sometimes
research program RT.
yes. I mean, I plan to go to do my master's from outside India. So I've also been looking into colleges and everything.
Just you can text me anytime if you have some doubt or anything
Oh, okay.
regarding preparation
Yeah.
and all.
Yes, thank you. That would mean a lot for me.
Great, great, lovely. Now, Mansi,
Yes, sir.
you asked अनन्या क्या खाया उसने?
Hi, Ananya.
Sorry, group.
How are you?
Hi, Mansi. I'm fine. How are you?
Oh, I'm also fine.
Also, you are in the same class with Indrani?
Yes, yes, we are from the same batch.
Okay. So this group is expanding. So your research group is really good.
Yeah, Hriday, you asked to Ananya whether she could make some friends or not. She could find some Indians or not.
Yes, sir. Hi,
Uh,
Ananya. How are you?
Hi, Vidhay. So there are many Indians.
How are you?
I'm fine.
Yeah, yeah. Are you from Assam?
I'm from Assam.
Okay.
In this group,
I'm also
everyone
from
is from
Assam.
Assam.
From
Okay.
yeah, yeah.
Hello, Ananya. I'd like to ask one question. Did you face any racism from the Americans, as we most commonly hear the cases?
No, no, no. These Americans are really sweet and quite helpful. Sometimes I feel they're better than the Indians who are staying in US. They're more helpful.
Uh, oh, all right.
Ananya already looks like white. Isn't it?
No, sir, I don't look like that.
Problem like me, people.
So no, the
So
people are really good.
yeah, that they have a better
Everyone is friendly.
outlook.
Professors are also
Yes.
friendly. Yes, sir.
Great. Yeah, diversity is very good there, na? Because other
Good.
many parts of the world people are there as a
Oh,
say,
people are
their
coming.
outlook is totally different. That is why it is a kind of inclusive approach is there. Yeah, in between Tausif has also joined. Welcome, Tausif. So Deep, would you like to ask anything? Oh, Ananya, ask me, just interact, yeah. I want to break this ice, na. Don't be, she's so, Ananya
Also,
is
I'd
so
like to
precious and
congratulate Himanshu Da. I'd like to congratulate
yeah,
Himanshu Da for completing his PhD thesis.
yeah. We are
Yeah.
waiting for his
Thank you very much, Ananya.
Welcome, Dada. So, Himanshu Da, are you now preparing for interviews and all?
Yeah, I have applied for the post of assistant professor in 5-6 places, but let me see what happens.
Okay. All the very best.
Yeah, thank you very much.
Yeah, if you find Ananya any suitable things for Himanshu, so please drag him there.
Yes, sir. Yes, sir.
So for PDF, even he will get fellowship more than whatever he will get as
Yes,
a
sir.
salary here in India.
Yeah, if
Okay.
there is any scope of postdoc there, please convey the message to me
Okay, sir.
if there is any
Okay.
place.
So Deep, yeah, Ananya, you wish to say something? Please tell. Complete
Like,
your sentence.
sir, in our university also, like many professors are taking out some positions for postdoc students. Like, I will just check,
Okay.
and if there is anything, I can share into the group only.
That shall be good. That shall be great help. Yeah, this is where now we have established a link through you. So Deep, Tashfin, Indrani is sorry, Ananya is here. Okay, so let us meet tomorrow. Thank you so much again, and best wishes. Happy time. Take care all of your health. Okay. Good night, and have a
Thank you,
great day.
sir.
Ananya.
Thank you.
Be in
Thank you,
touch.
sir.
Thank you, sir. Thank you, sir.
Thank you.